It's just a sound test. If you can hear well as, please answer yes in the chat box, please.
Good morning, everybody. Thank you all for coming to our webinar on sailing reliability for Kaplan turbines. I'm your moderator, Christine. Your host today is Isfan. He's Global Product Line Manager for EPS, which is Engineered Polymer Solutions. Isfan has a background in marine engineering, an MBA, and over 18 years of experience in the areas of heavy-duty hydraulic and pneumatic applications, including hydropower. If you have any questions, please type them into the chat or questions box, and we'll address them at the end. If you'd like to reach Isfan for technical assistance, you can email him, and I'll put his email address in the chat box. It's also istvan.hajzer@chesterton.com. And again, we can repeat that at the end. And with that, I'll turn it over to Isfan.
Christine, good morning, and thank you very much for your very warm intro. And in addition, this is my pleasure to welcome all of the participants as well. So actually, the main topic of this webinar today is how we can help our customers to optimize the Kaplan turbine reliability through the runner blade sealing solutions. Let's have a quick look at the agenda of the webinar of today. First of all, I would like to say a few words about the renewable energy sector, and then what is the situation of the hydropower in the renewable energy market, what is actually the trend in the hydropower market, what are the sealing challenges of the equipment, especially focusing on the turbines in the hydropower applications. Then, just from technical point of view, let's have a short discussion about the blade linear motion pattern and the blade droop questions. And then what are the typical OEM and aftermarket sealing solutions for the runner blade applications. And actually at the end, I would like to give you a short overview about the checklist, how we can actually go through the optimization of the runner blade linear seal application. And at the end, the summary, talking a little bit about the bathtub curve and demonstrate how we can help our customers to improve the reliability of such an applications. So the question is, why the green energy is so important. When we are talking about green energy, obviously we are talking about the renewable type of technologies. First of all, such a renewable technologies became mature, reliable, and providing virtually pollution-free solution in the energy sector. Reliability, from technical point of view, is an important point right now. And then this is a kind of an affordable energy, even in the emerging markets. Ensures sustainable access to the electricity, even if we have growing market demand for energy, and actually help to meet the goals on an overall pollution reduction to the energy sector. So when we are talking about the hydropower, why actually the hydropower is so important in the renewable energy sector? Because actually hydropower takes the largest share in this sector. The production of the hydropower segment is around 80% of the global renewable energy, and this is more or less 15% of the total electricity generation on the global level. This 15% actually means and representing around 3,000 terawatt hours power generation in a year. This is a large number, but most important to understand that actually we are still far away from the real potential what is represented by the hydropower and what actually potentially can be utilized in the future. Because in the reality, the potential energy what we can generate through hydropower in the future is something like 16,000 terawatt hours per year, meaning this is 5 times more what we utilize today. What does it mean for us? Number one, we can expect much more investments in hydropower, in new hydropower plants in the future. And the second aspect is that actually we can expect much more projects in the future in the rehabilitation of the existing hydropower plants. And the main goal is going to be to improve the efficiency and actually to increase the output of the existing plants as well. There are several advantages of the hydropower systems among the green power technologies. One, first of all, the hydropower is actually provide a quick response to the demanding fluctuation in the system, meaning that actually it helps to stabilize the grid. Number two, the flexibility. The hydropower power generation is extremely flexible, balancing between the energy generation and the demand, which is actually actual in the system. It's a large scale and long-term energy storage through the reservoirs of the hydropower plants. Extremely cost-effective solution, and in the reality, the hydropower is a CO2-free operation, so it's extremely environmental friendly technology. When we are talking about the hydropower industry, we have to take into consideration several aspects, and this is going to be technical aspect. Number one, that the shutdowns are rare, so the reliability and the availability of the equipment must be extremely high. Number two, the overhauls and the refurbishment can stretch over decades. So again, the performance of the equipment and the performance of the products what are used in such an hydro equipment are extremely important. Some other aspects, and just let me give you some bullets. Heavy-duty hydraulic applications, in most of the cases what we are talking about in case of hydro applications. Difficult operational conditions, high pressure, and typically what we are talking about, harsh environment, heavy components and heavy equipment, difficult access for the equipments and to the seals. So it means that even just a seal replacement could be a real problem and could take for a long time, meaning that the time for the repair is relatively long. And erosion, corrosion, plus vacuum, what we have to take into consideration in case of most of the hydropower applications. The hydropower technology itself is actually known as an environmental friendly technology, and this is a pollution-free pattern. However, still hydropower represents a certain level of risk to the environment because of several reasons. Number one, we use different lubricants and hydraulic fluids in the system. First of all, to equalize the pressure to the outside water pressure, and we are talking about the equalizer pressure, and we are talking about the pressure inside of the turbine hub. And then many of the driving and positioning functions obtained by hydraulic or by pneumatic systems, meaning fluid power system in general, where we have to use a certain type of a media. And the lubrication of the moving components in the system. And altogether, it means there's a high volume of oils and lubricants, including grease, what are going to represent such a risk to the environment. As actually there is an increasing demand on the water quality and in the water quality preservation, obviously the water pollution prevention is getting more and more important, meaning that actually the hydropower plants must work leak-free and no downstream pollution is actually allowed at all. When we are talking about the hydropower industry, there are three major types of turbines are used in those technologies. First is the Kaplan turbines, and Francis and the Pelton. Obviously, the turbines are used in different shapes, depending on the operating condition or operating conditions of the hydropower plant itself. But today we are going to focus on the Kaplan turbines, and the reason is because Kaplan turbines represent the most complex hydraulic and pneumatic systems, where we have to focus on the reliable sealing solutions. Let's have a look at a typical Kaplan turbine. And this turbine is actually a double regulated turbine system, meaning double regulating, that we regulate the position of the wicket gates, and then we actually harmonize the position of the runner blades to the wicket gate positions. What kind of seal fluid power and lubrication type of applications we are talking about in case of Kaplan turbines? First of all, the brake and jack cylinders next to the generators, the wicket gate stem sealing and bearing applications, the blade pitch cylinder runner blade trunnion seal. Then we are talking about the generator and the turbine main shaft bearing application, servo motors for the wicket gates, distributor ring, and the control linkage to the wicket gates. So all of them are somehow related to fluid power systems or lubricated bearing applications. What is the trend on the market today, taking into consideration that actually the hydro plants must be more environmental friendly? The first possibility to reduce the risk of the downstream pollution is actually to reduce the amount of the oil or the lubricants what are utilized in the systems. And what we can see, especially in the last 2 decades, is that many of the turbine manufacturers and even companies who are involved in rehabilitation of the existing turbine systems are moving from the low pressure hydraulic systems to high pressure systems, meaning that through the high pressure, they can actually reduce the size of the units, hydraulic units in the system, meaning that smaller units, like smaller hydraulic cylinders, are going to need less oil in the system. So in overall, the total volume of the oil, for example, if it is a hydraulic oil, can be reduced. The second possibility, and this is again a kind of a trend, that in many applications, actually customers move from the traditional petroleum-based oils, and they replace the oils by biodegradable, environmental friendly fluids, just like with water or water glycol mixture. And another opportunity is that they replace the petroleum-based oils by air, and in the turbine hub, actually they utilize electric servo motor and self-lubricated bearings instead of hydraulic system and instead of oil or grease lubricated bearings. And the last thing is, however, is going to be the most important from sealing technology point of view, that everybody is moving in the direction to try to mitigate the risk of the oil leakage in order to reduce the risk of the downstream pollution. And just let me give you one example through the picture where you can see actually a hydrostatic water guide bearing where they use filtered pressurized water. So it means that actually the lubricant to the bearing is the water itself, the filtered river water itself, what they take from the penstock. So here the lubricant is water and not oil or not grease anymore, as it was actually the traditional solution in the past. In 2006 and 2007, a kind of an industrial survey was made in Canada, and this survey was made among the hydropower owners, and the interesting result is that actually in most of the cases, and most of the cases mean actually 16%, actually the downstream pollution and the problems to the hydropower owners was caused actually by the Kaplan turbine runner blade seal leakage. So 60% is a significant number. It means that actually we have to really focus on a reliable sealing solution for the Kaplan runner blade application. And if we provide a reliable solution, we can solve at least 60% of the problems to the hydropower owners and operators. While in case of changing from oil lubricated system to air, or we're changing from oil lubricated system to water or water glycol, actually such a possibilities are much more where the customer is doing or ordering the new turbines or doing the rehabilitation of the existing units, while the reliable sealing solution is actually the area much more to focus on, where there is no possibility for the overhauling, there is no possibility for the rehabilitation, which means that actually the turbines are still in operation. What are the typical sealing challenges related to the Kaplan runner blade turbine sealing applications? There are several direct and indirect challenges. First of all, improve the mean time between the repair, which is actually the typical area of the equipment performance metrics, the MTTR, MTBF area. MTTR, the mean time to repair, and MTBF is actually the mean time between failure. the obvious desire by the customers is actually to improve and prolong the lifetime of the seals in such applications. The second point is the installation. The installation of the runner blade trunnion seals are extremely difficult, especially on site. So customers are looking for solutions where actually the simplified installation going to help them to reduce the repair time, to reduce the installation time of the seals, and reduce the risk of the failures during the installation. Overall, reduce the maintenance cost of the hydropower equipment and turbines, minimize the downtime through the simplifying installation of the seals, and positively impacting the environment, protecting actually against possible pollution. So with the Kaplan turbines in particular, the runner blade seal plays a key role in the maintaining reliability, efficiency, and actually to protect the environment from the oil leakage. That's the reason why we have to focus so much on the runner blade trunnion sealing application. Before we move to the discussion about the sealing, just let me give you a very short overview about the runner blade motion pattern, because this is very important to understand what kind of an influence actually this motion pattern has on the sealing and the sealing technology that is really going to provide the reliable solution. The Kaplan runner blades have a very slow speed and an extremely low frequency of oscillation. But in the reality, in most of the time, in most of the operating time, actually the blades are in a standstill, or let's say much more in a kind of a static operating mode. However, even if we have such a very low frequency and we have a very low speed, through the long years of the operation of the turbines, the accumulated number of the cycles can achieve around 60,000, which is a relatively high number. So even if it is a slow speed application with a very low frequency, at the end the accumulated number of the cycles is actually high. Just giving you an idea, and this is the chart on the slide. What you can see, this is a kind of a simulation of the runner blade motion, and as this is actually is coming from Voigt Hydro. This is how they simulate the operation of the blades, and as you will see the oscillation in most of the cases, and this is going to be something like 70% of the cases, the oscillation is within plus minus 3 degrees, while around 27% the oscillation motion is going to be around plus minus 5 degrees, and just in less than 3% of the cases, the blade is going to move actually plus minus 45 degrees. Meaning that actually the blade in most of the cases, as we have already discussed, in static operating mode, and actually in most, if they have to move, normally just they adjust the blade position, and this is around maximum 3 degrees. Why it is important to emphasize that it's static, and if we have the oscillation, that is going to be in most of the cases just something like plus minus 3 degrees, because in such a static type of an operating mode, if we have a full contact between the seal and the counterface, which is actually the metal face. What you can see here on the picture, the blue area is actually the seal surface, while the black area is actually the metal itself, the counterface where we have the contact. And as the seal is flexible, and this is in a static operating mode. There is no relative motion between the counterface and the seal. We have a full contact, and the elastic seal material try to conform to the irregularities of the seal. So there will be no lubrication between these two surfaces. This is what we call the boundary friction. In case of slow speed application, which is typically the oscillation with a very low speed and with this ±3 or ±5 degree, we can expect a kind of a mixed friction. As you see in the picture, actually we have more lubricant, more fluid between the surfaces, but still is not completely lubricated. And the last one is the liquid friction, where we need a certain speed, a certain velocity, relative speed between the counterface and the seal in order to create a full liquid or oil film between the surfaces. So actually, the runner blade seals are operating in the boundary friction or just in the mixed friction area, but they are never fully lubricated. And if we have a chart, if we have a look at the chart, how the frictional force is changing by the speed, you will see that actually the frictional force is the highest when the relative speed is zero between the surfaces. So if the frictional force is the highest, it means that at the same time the wear is going to be the highest. As soon as the velocity is increasing, we get into the mixed friction area, and the frictional force is gonna be reduced, and the wear is gonna be reduced, while thanks to the internal resistance of the fluid against the flow, then at a higher speed the friction is going to be increased again. But the most important is, as in most of the cases we have zero speed or very low speed, but actually the seals in such a turbine applications are operating in the boundary or in the mixed friction area where the friction and the wear out is actually the highest. The second technical aspect is actually the blade droop itself. The blade droop is actually the eccentricity of the blade shaft itself compared to the bearings. Why we have blade droop? Number one, there are manufacturing tolerances and running clearances of the machine components, including the bearings, the bushings, and the trunnions. So this is a kind of an obvious droop of the blade itself. The second aspect is that the blades are usually heavy. We are talking about a couple of tons, especially in large sized turbines. And actually, the gravity force try to move the blades out from the center line. The third point is that some of the bearing materials what are used in the turbine, in the blade runner blade trunnion seal, in the runner blade trunnion applications are actually relatively soft. So that means soft that actually the Young's modulus relatively low. So if we have relatively high load in the bearings, just because of the low Young's modulus of such a materials, deformation gonna be occurred under load, thanks to the weight of the blades. Plus, the reaction force what is generated during the operation of the turbine is going to try to move the blade trunnion axis out from the center line of the bushings. Plus, and this is one of the most important aspects, is actually the wear out of the blade trunnion bearings, because as we discussed before, in most of the cases we have static or actually very slow speed motion, and the bearings are going to work exactly in the same way as the seals are working, meaning that there will be no lubrication. So actually the bearings are gonna face boundary or just mixed lubrication during the operation. That's the reason why actually the wear out of the bearings are relatively fast. Just a few examples, what you can see actually on the pictures. Several Devon blade trunnion bushings on the left hand side after a few years operation, thanks to the fact that there is no proper lubrication and there is no possibility that the oil film would build up between the trunnion and the bearing itself. Actually, on the right hand side, you can see from the same application, from the same turbine, the trunnion itself. And the interesting thing is that you see the color of the surface has been changed, and this is brownish. Why? Because the bronze transferred from the bronze bushing to the surface of the trunnion itself, meaning that there was a high friction and a high excessive wear between the trunnion and the bushing surface. So, what are the common blade runner trunnion sealing associated issues? Number one, failure to keep the water or the contaminants out of the hub, meaning that the water and the contaminants can actually ingress into the hub, causing hub of the turbine, causing several issues. The second is the failure to keep the oil in the hub, and this is actually can be caused by the poor sealing, due to the poor sealing, or by the poor design, or by the material what is used for the production of the seal. And a typical problem is that actually in many cases customers do not take into consideration the blade droop itself, especially not in turbines what are in operation for a longer time. But the blade droop actually itself has significant impact on the seal itself, because the radial overload can be occurred just because of this blade droop. On one side the radial overload, while on the opposite side we can expect radial opening, too much opening of the seal. So most probably, if the seal is not flexible enough, even cannot compensate such an opening, and actually the excessive deformation and the friction just because of the radial overload on the seals. Some of the typical solutions from the past, OEM and aftermarket solutions. What is common with these seal solutions? They utilize rubber compounds, where actually rubber compounds have high coefficient of friction. Number one. Number two, the elasticity is elasticity of the material is limited, and the elastic memory is relatively short. So they actually have to energize the seal somehow. One possibility is actually the mechanical compression, or even in some cases they use spring systems to energize the seal just to provide the sealing, the positive sealing through the seal. Then actually this is a relatively, on the previous slide we've seen relatively old solutions, and what we can see today is, number one, most of the solutions that are used by the turbine OEMs and but used by the end users are actually based on rubber. But much more, they move in the direction to use a kind of a packing or a chevron stack set in a back-to-back configuration. And actually, such a stack sets have to be compressed, mechanically pre-compressed before the turbine is back to operation. On this slide, we will see another solution, but actually traditional stack sets are in back-to-back configuration. In the last two decades, actually the polymer-based technologies are became more popular. So what we see is that from material technology point of view, we move from rubber to polyurethanes. But still we have some but still the customers have some issues with the polyurethanes. One problem is actually the hydrolysis resistance of the polyurethanes. The second thing is a relatively high friction, and then the seal solution what are offered by most of the seal manufacturers are actually relatively difficult to install. What you can see on the pictures here is that the seal itself is split, but directly before the installation in the seal cavity, the seal itself actually have to be welded, and this is on site, especially on site, is a difficult process, and that is a post-treatment what has to be done. So this process itself is relatively difficult, and there is a high risk of failure during the welding process itself. So just a few words about the construction of a good runner blade seal, what we actually recommend to use. First of all, it has to be a back-to-back configuration, because the runner blade seal must have two functions. First is actually to keep the lubricant or keep the oil in the hub itself, and the other one is to keep the water and to keep the contaminant out, not let to ingress it into the hub, because it really is going to create problems. The second important attribute is that the profile lip seal has to have flexible lip design, and I'm going to explain in a minute why the flexibility is so important. And then the third attribute is actually to compensate the runner blade trunnion bearing wear out, which is actually the blade loop itself, because the proper seal design is going to provide the capability to the seal to compensate the blade loop. So actually, even if we are talking about worn bearings, relatively excessive blade loop, the seal is going to provide tight sealing. Just let me give you show you two configurations. On the left-hand side, there is a touring back-to-back configuration, and this is typically used when we have enough space in the stuffing box. In several of the cases, just because of the design of the seal stuffing box itself, the space is short, so there is no possibility to install two seals in the back-to-back configuration. In such a case, the right solution is to have a one-ring solution, which is actually a double-acting seal, but still it is actually going to provide sealing on one side to keep the oil in and to keep the water out. And this is one-ring solution for short stuffing boxes. Axial compression is important point, because we have to lock the seal in the stuffing box, and we have to protect the seal against rotation, possible rotation again together with the trunnion. And the axial compression is going to actually energize the static lip of the seal, providing tighter sealing in the stuffing box. And the multiple sealing point is important point as well, because in many cases we see that the surface finish, the surface condition of the stuffing box is not perfect. What can be the reason? Sorry for that. What can be the reason? Corrosion, erosion of the surface, or actually physical damages. Made to order, the geometry and the dimension of the seal is according to the actual hardware sizes, because there can be deviations, and very important to have a solid seal material which is going to help to make an easier installation and to prevent excessive stretching or twisting during the installation, because this is one of the typical problems what we see in case of stack sets, or when customer actually install the O-ring, then during the installation the O-ring is twisting in the rope. High performance thermoset polyurethane material is going to help to improve the lifetime of the seals, because such a thermoset polyurethanes have extremely high abrasion resistance. There is a high tensile strength, which is going to provide the mechanical strength of the seal material itself. self-lubricated material for low coefficient of friction. So if the friction is low, then the wear is going to be low, and no aging, no material degradation, and even the shelf life of the seal is something like, and the material is something like 25 years. In the two charts, we compare the coefficient of friction where the polyurethane has 0.2 compared to the rubber, which is actually in the range of 1. So this is 1/5. And on the right-hand side, we compared the typical characteristics of abrasion resistance of polyurethane and rubber, and the polyurethane has much higher abrasion resistance, which is extremely important in case of an application where the seal is going to face boundary or mixed lubrication. Split is extremely important. Actually, how easy to install the seal, and what you can see is that the real mechanical split seal design not needed any kind of a complicated gluing or welding process, just actually to close the joint and push the seal into the seal cavity. So the process itself is simple and easy. There is no risk of any kind of a possible failure during the installation. And just the checklist, what we recommend to take into consideration when you make the selection and the design of the seal. Get exact turbine blade measurement. This is important because actually there are no international standards, there are no real recommendation specifications are available in the market. So there is a very high variation of different stuffing box sizes on the market. Checking the seal cavity cross section and the values, because even just because of the wear out of the bearings, the blade loop value can vary by blade even in the same turbine. And just one example is how we do and how we recommend to do actually the measurements and to record the measurements by blades. As you see in the chart here, there are eight blades, because this Kaplan turbine has eight blades, and we measure actually the blade loop by blade itself. Check and resolve equipment condition, typical problems, mechanical damages, scratches, scores, wear out of the counter surface just because of the high friction, and the high friction cause a wear out, or fretting, abrasion by the solid particles in the water, in the river water, especially in the low water head hydropower plants, corrosion, pitting corrosion by the water. And just two examples. One is actually on the left-hand side, is a good example how is the seal cavity surface is corroded. On the right-hand side is a fretting caused by the high friction rubber seal in the stuffing box. Plus, we have to take into consideration fluctuation of the turbine pressure. So that's the reason why the seal has to have very flexible sealing, because actually the seal has to react according to the pressure situation, what is varying. Vibration and cavitation. Again, here, such a typical problems where we have the answer with the flexible seal design and with the long elastic memory seal material, and can withstand for the longer life. Low water head shame, and this is what I mentioned before, that especially in the low water head, there is a very high risk of abrasive contamination of the water just by the sediments, just like the mud, and this has a high wear on the seals. So just at the end, let me summarize how actually the reliable seal solution can help to improve the reliability of the turbine itself. You can see on the slide actually the bathtub curve, and the bathtub curve demonstrates the probability of the failure based on the operating life. So actually, when the customer put in operation the turbine itself, the risk or the probability of the failure is high. Why is that? it could happen that there is a quality issue of the component what they install in the turbine. Or there is a possibility that they make mistakes during the installation, and for example, they damage the seals. So actually, this is one area where we can help to our customers to reduce the probability or the risk of the failure, because with the split interlock seal, with the real mechanical split seal, we can help to make the installation easy and to avoid any kind of mistake during the installation. On the other hand, of the bathtub curve, which is actually the wear out failure mode area, we can help to prolong the lifetime just because of the lower coefficient of friction, because of the lower wear rate, and because of the longer elasticity and the elastic memory of the seal material. So help to your customers at the beginning when they put it in operation, and help to the customers in the wear out failure mode area to prolong the lifetime. This is actually the essence how we can help to our customers to improve the reliability of the turbines. Thank you very much for your kind attention. And if there is any kind of a question, we are more than pleased to answer them.
Yes, thank you very much, Isfan, for your great presentation. We'll take questions now if you have any. We did run a little over, and I apologize for that, but we will be sending out the presentation and the recording if there's anything that you had missed.